What is the most violent explosion in the universe? You might think of a volcano, a mountain blowing its top, sending ash and rock for miles. That's violent. Or maybe you think of a nuclear bomb, the kind of power that can level a city in a flash. That is certainly a violent explosion. We have a frame of reference for that. We can measure it in tons of TNT. We understand its destructive force. On a human scale, it's the ultimate explosion, but the universe doesn't operate on a human scale. Our most powerful weapons are like firecrackers in a hurricane compared to what happens in space. To find the most violent explosions, we have to look out, far away from our quiet little neighborhood. We have to look at the death of stars. For a long time, the answer to this question seemed simple. It was a supernova. A supernova is the end of a star's life. It's a final spectacular burst of energy. And for a star, death is a very violent process. There are a couple of main ways a star can go supernova. The first way happens to truly massive stars. We're talking stars at least 8 times more massive than our own sun. These stars live fast and die young. Throughout their lives, they are giant fusion reactors. They fuse hydrogen into helium, then helium into carbon, and so on, creating heavier and heavier elements in their core. Each stage of fusion releases energy. This energy pushes outward, fighting against the star's own immense gravity, which is trying to crush it. It's a delicate balancing act that lasts for millions of years, but eventually the star creates iron in its core. And this is a dead end. Fusing iron doesn't release energy, it consumes it. Suddenly, the outward push from fusion stops. The furnace goes out. In that instant, gravity wins. It wins catastrophically. The star's core collapses. In less than a second, a region the size of Earth collapses down to the size of a city. The temperature and density skyrocket. The core becomes an incredibly dense ball of matter. The outer layers of the star, which were also falling inward, slam into this newly formed, super dense core. They bounce off it. This rebound creates a shockwave of unimaginable power. The shockwave tears through the rest of the star, blasting its outer layers into space at incredible speeds. This is a supernova. For a few weeks, this single exploding star can outshine its entire galaxy, a galaxy containing hundreds of billions of other stars. The energy released is staggering. It's more energy than our sun will produce in its entire 10 billion year lifetime. All of it released in a matter of days and weeks. This explosion forges even heavier elements and scatters them across space. The carbon in your body, the oxygen you breathe, the iron in your blood, it was all created inside a massive star and flung into the cosmos by a supernova. We are literally made of stardust from these explosions. There's another type of supernova too. This one happens to smaller stars, like our sun. When a star like the sun dies, it doesn't explode. It's not massive enough, it just sort of puffs its outer layers away and leaves behind a small, hot, dense core called a white dwarf. A white dwarf is about the mass of the sun, squeezed into the size of the Earth. It's incredibly dense. But if that white dwarf is in a binary system, meaning it's orbiting another star, it can have a second life. Its powerful gravity can start pulling material, mostly hydrogen and helium, off its companion star. This material builds up on the surface of the white dwarf. Over thousands of years, the white dwarf gets heavier and heavier. It approaches a critical limit, a specific mass known as the Chandrasekhar limit. It's about 1.4 times the mass of our sun. Once it hits that limit, the pressure inside the white dwarf becomes too great. A runaway chain reaction of carbon fusion begins. The entire white dwarf detonates in a thermonuclear explosion. This type of supernova is also incredibly bright because they all explode at the same mass. They all have roughly the same brightness. This makes them very useful for astronomers as standard candles to measure vast distances across the universe. So, for decades, supernovae were the champions. They were the biggest, most violent explosions we knew of. They create the elements of life. They can be seen from billions of light years away. They seem to be the ultimate cosmic firework. But we were wrong. There is something else. Something far more violent, something so powerful it almost defies comprehension. The story of their discovery is a strange one. It begins during the Cold War. In the 1960s, the United States launched a series of satellites called the Vela satellites. Their job was not to look at the stars, their job was to look at the Earth. They were designed to detect flashes of gamma rays, the most energetic form of light. The purpose was to make sure the Soviet Union wasn't testing nuclear bombs in space, in violation of a treaty. These satellites did see flashes of gamma rays, but they weren't coming from Earth or anywhere near it. They were coming from random directions in deep space. They were short, intense bursts of energy. They would last for a few seconds, or maybe a minute, and then vanish without a trace. The signals were a complete mystery. The information was classified for years. Scientists were baffled. What in the universe could produce such a powerful burst of pure gamma rays? When the data was finally declassified in the 1970s, astronomers started calling them gamma ray bursts, or GRBs. For a long time, we had no idea what they were. We didn't know how far away they were. If they were close, within our own Milky Way galaxy, they might be from some strange type of star. If they were far away in distant galaxies, then their true energy must be absolutely mind-boggling. To be visible from billions of light years away, the source would have to be brighter than a supernova. Far, far brighter. The mystery was finally solved in the 1990s. A satellite called the Compton Gamma Ray Observatory was able to pinpoint the locations of these bursts with more accuracy. When telescopes on the ground quickly looked at those locations, they found the faint afterglows of the explosions. And those afterglows were located in extremely distant galaxies, billions of light years away. This was the bombshell. The GRBs were not in our backyard, they were among the most distant events ever observed. And that meant the amount of energy they were releasing was almost unbelievable. Here's a way to think about it. A typical supernova, as we said, releases more energy than our sun will in its entire 10 billion year lifetime. A typical long gamma ray burst releases about 100 times more energy than a supernova. And it releases most of this energy not over weeks, but in a matter of seconds. Let that sink in. In 10 seconds, a GRB can release more energy than our sun will produce over its entire existence. It is the most concentrated, most powerful, most violent release of energy in the universe since the Big Bang itself. A supernova is a firecracker. A GRB is a stick of dynamite the size of a planet. So what could possibly cause something like this? What kind of cosmic engine can generate so much power so quickly? It turns out there are two main types of gamma ray bursts, and they have two different but equally terrifying origins. First, there are the long-duration GRBs. These last for more than 2 seconds, sometimes for several minutes. These are now believed to be a very special and very rare kind of supernova. They are sometimes called a hypernova or a collapsar. It starts with a truly gigantic star, not just a massive star like the kind that makes a normal supernova. We're talking about a star that is maybe 30, 40, or even 100 times the mass of our sun. And it has to be spinning very, very fast. When a star like this runs out of fuel, its core collapses, just like in a normal supernova. But because the star is so massive, the core doesn't stop and form a dense ball of neutrons. And gravity is too strong, the core collapses all the way down into a black hole. So now you have a brand new spinning black hole at the center of a dying star. As the rest of the star's material rains down on this black hole, it forms a swirling, superheated disk of matter around it called an accretion disk. The combination of the black hole's rapid spin and powerful magnetic fields creates an enormous cosmic engine. This engine funnels a huge amount of energy and matter into two tightly focused, high-speed jets. These jets, moving at more than 99.9%, the speed of light, are like cosmic drills. They blast their way out from the core of the star through all of its outer layers. When these jets finally break free from the star's surface, they shoot out into space. It is these jets, these focused beams of pure energy and matter, that we see as a gamma ray burst. The rest of the star then explodes in a supernova-like event, but it's a supernova on steroids, supercharged by the central engine. The key here is the jets. A GRB is not a spherical explosion like a bomb going off in all directions. It's a focused beam like a lighthouse or a searchlight. This is crucial. It explains why they are so incredibly bright. All of that mind-boggling energy isn't spread out over a huge area. It's concentrated into two narrow cones. If one of those cones happens to be pointed directly at Earth, we see an incredibly bright flash of gamma rays. We see a GRB. For every one GRB we see, there are probably hundreds more going off that we miss, simply because their beams are pointed in other directions. So that's the long GRB, the death of a colossal spinning star giving birth to a black hole. It is the undisputed champion of violent explosions from a single object, but there is another kind. The short-duration GRBs, these are flashes that last for less than 2 seconds. For a long time, their origin was also a mystery. They seem to happen in different places than long GRBs, sometimes in older galaxies where massive stars no longer exist. What could produce so much energy in such a short time? The answer is even more exotic. It involves not one dead star, but two. The culprit here is the collision of two neutron stars. A neutron star is what's left behind after a massive star. One not quite massive enough to form a black hole goes supernova. It's the super dense core we talked about earlier. Imagine taking 1.5 times the mass of our sun and crushing it into a sphere only about 12 miles across. A single teaspoon of neutron star material would weigh billions of tons. They are the densest objects in the universe, besides black holes. Sometimes, two massive stars are born together in a binary system. They both live their lives, and they both eventually explode as supernovae, each one leaving behind a neutron star. So now you have two neutron stars orbiting each other. For millions or even billions of years, they circle each other in a silent cosmic dance. But their dance is doomed. As they orbit, they radiate energy away in the form of gravitational waves, ripples in the fabric of space-time itself. Einstein predicted these waves a century ago, and we first detected them directly in 2015. This loss of energy causes their orbit to shrink. They get closer and closer, spinning faster and faster around each other. In the final moments, they are orbiting each other thousands of times per second, moving at a significant fraction of the speed of light. Then they collide, they merge. This merger is an event of almost unimaginable violence. Two of the densest objects in the universe, each with more mass than the sun, smashing into each other. The collision likely creates a black hole in an instant. It also unleashes a huge burst of energy, including a very short, very intense flash of gamma rays. This is the short GRB. The collision does something else too. It rips off some of the neutron star material and flings it out into space. This material is incredibly dense and hot. As this cloud of exotic matter expands and cools, it undergoes a whole series of nuclear reactions. This process, called R-process nucleosynthesis, is where most of the heaviest elements in the universe are born. The things like gold, platinum, and uranium. For years, we weren't sure where all the gold in the universe came from. Supernovae can make heavy elements, but not enough of the really heavy ones. The neutron star merger model predicted that these collisions would be gold factories. In 2017, we saw it happen. The LIGO Gravitational Wave Observatory detected the ripples from two neutron stars merging. Telescopes all over the world quickly turned to that spot in the sky. They saw the short GRB. And in the days that followed, they saw the fading glow of the ejected material, an event called a kilonova. By analyzing the light from that kilonova, astronomers confirmed that huge quantities of heavy elements, including gold and platinum, were created in the crash. The gold in a wedding ring was very likely forged in the cataclysmic collision of two dead stars. So we have our answer. The most violent explosions in the universe are gamma ray bursts. Whether it's a long GRB from the collapse of a titanic star or a short GRB from the merger of two neutron stars, they represent a release of energy that dwarfs anything else we see. But are there any other contenders? It's worth considering a couple of other cosmic phenomena just for scale. What about quasars? You may have heard of them. Quasars are the intensely bright cores of very distant young galaxies. A quasar can be trillions of times brighter than our sun. It can outshine its entire host galaxy. That sounds pretty violent. The power source for a quasar is a supermassive black hole at the center of the galaxy. Not a black hole with the mass of a star, but one with millions or even billions of times the mass of our sun. As gas, dust, and even whole stars fall into this monster, they form a huge, hot, glowing accretion disk. The friction and gravitational energy release a colossal amount of radiation, making the galaxy's center blaze with light. So, is a quasar more violent than a GRB? It's a different kind of violence. A GRB is an explosion. It's a single brief cataclysmic event. A quasar is a process. It's a continuous, sustained release of energy that can last for millions of years. In terms of total energy released over its entire lifetime, a quasar wins, no contest. But in terms of power, which is energy released per second, a GRB is the champion. A GRB is a flashbulb. A quasar is a searchlight that stays on for eons. For a few seconds, the flashbulb is much, much brighter. Then there is the ultimate event, the Big Bang. Wasn't that the biggest explosion of all time? This is a common way to think about it, but it's a bit of a misconception. The Big Bang wasn't an explosion in space, like a bomb going off at a particular point. It was the beginning of space and time itself. It was an explosion of space. Every point in the universe was part of that initial moment. The universe didn't expand out into a pre-existing emptiness. The universe itself expanded, carrying everything with it. So, in terms of the total energy involved, yes, the Big Bang is in a category all its own. It contained all the energy that would ever exist in our universe, but it's not a localized explosion that you could stand back and watch. It's the event that created the very concept of standing back and watching. So, when we ask about the most violent explosion in the universe, we're usually talking about events that happen within the universe as we know it. In that context, gamma ray bursts hold the title. The existence of these events has profound implications. First, they are part of the great cosmic cycle of creation. Supernovae and neutron star mergers create and distribute the heavy elements necessary for planets and for life. Without these violent deaths, the universe would be a boring place, made of almost nothing but hydrogen and helium. There would be no rocky planets, no water, no people. The violence of yesterday is the reason for our existence today. But there is a darker side. What would happen if a gamma ray burst went off in our own galaxy, and its jet was pointed right at Earth? The results would not be good. Even from thousands of light years away, the sheer intensity of the gamma rays and other radiation would be devastating. It would be like getting a lethal dose of radiation from a cosmic shotgun. The radiation would fry any satellites and astronauts in orbit. More seriously, it would hit our upper atmosphere and trigger chemical reactions that would destroy the ozone layer. Without the ozone layer to protect us from the sun's ultraviolet radiation, life on the surface would be in serious trouble. It could cause a mass extinction event. Some scientists have speculated that a past mass extinction on Earth might have been caused by a nearby GRB. It's a sobering thought. We live in a universe that is not only beautiful, but also incredibly violent. We are lucky to be in a quiet, stable part of our galaxy. The universe is a big place. The chances of a GRB being aimed directly at us from a dangerous distance are very, very small. But they are not zero. It's a reminder of the immense power that is constantly being unleashed across the cosmos, far from our perception. And so, the most violent explosion in the universe is a gamma ray burst. It is a fleeting, focused blast of energy from the death of a giant star or the collision of two stellar corpses. It is an event so powerful, it can be seen from the edge of the observable universe. It is a creator of gold and a potential destroyer of worlds. It is a beautiful, terrifying testament to the extremes of physics. And it is a reminder that even compared to our most destructive creations, we are small, and the universe is vast, powerful, and still full of mysteries. We've only been watching the sky with the right tools for a short time. Who knows what other, even more violent, phenomena are waiting to be discovered?